Hello everyone, and welcome to my presentation on forward stratigraphic modelling of mass transport deposits in the Brazos-Trinity Basin IV, Gulf of Mexico, and their implications for hydrocarbon development. I would like to thank my supervisors Cedric John, Sarah Robinson, Mike Simmons and Andrew Davies for supervising this project. So what are the aims of this project? They are to produce forward stratigraphic models using Davies flow and Cougar flow in order to understand the links between use-to-sea and mass transport deposits, and therefore evaluate the implications MTBs have on hydrocarbon exploration and development. How did I go about this? I used biostratigraphic data to produce a Pleistocene bathymetry and produce an experimental design, and therefore conducting an uncertainty analysis using Cougar flow. The first hypothesis incorporates the fact that MTBs occur during low-span system tracts of stratigraphic sequence cycles. This is based on the widely accepted Vail 1993 model. Second hypothesis incorporates the fact that use-to-sea is the dominating control on MTB sedimentation in Basin 4, with factors such as sediment supply, delta position and width providing those secondary influences. So the main workflow incorporates the regional understanding, the design experiment, and finally the conclusions, including the hydrocarbon implications. The main study area and dataset. Where is Basin 4 located? So it's located in the northwestern area of the Gulf of Mexico, and the main sediment sources come from the two rivers, the Brazos-Trinity rivers. So I'm specifically interested in Basin 4 and capturing its sediment flux. Therefore, my strategy was to capture the coastline through the regional model outlined in red, allowing the sediment flux of Basin 4 within the nested model outlined in blue to be estimated. The main dataset was a compilation of wells made by Shell supplied by Halliburton and the IODP Expedition 308 wells, which incorporated the Fashi's calibration, the sediment provenance, and geometries. What were the main input parameters for my models? So Model A, the regional model, incorporated much larger size than Model B, the nested model, of 600 times 600 kilometres compared to 75 times 75 kilometres. The duration was during the Pleistocene. So I utilised the Miller 2020 sea level curve and utilised the Galloway et al. 2009 papers for sediment supply and fluvial discharge. Grain size classes came from the Davies flow workflow, and the diffusion coefficients were tested utilising the regional model and the nested model, utilising Howie et al. 2009 papers. So the regional structural history, what's happening during this time period? From the Paleocene to the Middle Eocene, we had the Larimide thrusting and drainage along the southern axes. From the late Eocene to the Oligocene and the Miocene, we had volcanism uplift. This was the same story from the Pliocene to the Pleistocene, incorporating the first impact of glacial eusticity and the high-frequency eustatic sea level fall, with routing along the Red, Mississippi and Tennessee rivers. And finally, during the Holocene, we had loading subsidence, halokinesis and transgression up to present-day sea levels. So these three images indicate the MIS stages. So from MIS 5E to MIS 1 incorporates the whole eustatic cycle. So the most prominent impact you can see here is during MIS 2 at maximum low stand. During the last glacial maximum, we had the two deltas and the main rivers reaching the maximum progradation at the shelf edge and the maximum sediment influx into Basin 4. So the nested model evolution. What did the two basins, Basin 2 and Basin 4, look like and evolve throughout? So older than MIS 5D at 140,000 years ago, we can see this was what it would have looked like before sedimentation started. During MIS 5, between 129 and 45,000 years ago, we had the influx of hemipelagic and muddy sediments, creating ponded accommodation in Basin 2 and Basin 4. During MIS 2 to the maximum load stand, we have the influx of mainly sandy sediment and sandy turbidites, and this can be seen here. Use-to-sea and biostratigraphy. What were the previous studies? Armentrout in 1996 looked at the biofasces response in East Breaks, and this can be seen in these two diagrams, 3.1 MA and 2.8 MA. So during maximum low stand at 3.1 MA, we saw the basinward incursion of the biofasces. So the basinward incursion of the altoneritic and upper bathyal fasces. This was the opposite during high stand at 2.8 MA, which saw the retreat of the biofasces back to shore. So I utilised the Miller 2020 eustatic curve, and this shows the full eustatic cycle from 140,000 years ago to the present day. So you can see labelled, we have the low stand, the early falling stage, down to the falling stage sea level, which is punctuated by a period of high frequency regressions during the influence of the Milankovitch cycles. And then at 20,000 years ago, we have maximum low stand, and then the sea level quickly increases and up to present day sea level. So the experimental design. I made 7 models. So models A and B are the previously mentioned regional and nested models. Models C and D tested the sensitivity of the Miller 2020 sea level curve. Models E and F looked at the impact of a doubled sediment supply compared to a fluctuating sediment supply. And Model G tested the impact of increased storm frequency, with Model 8.1, the Cougar flow experiment for the regional model. So the fast use definitions were incorporated from the Darwin assessment workflow. And our workflow incorporates the well log data, geological model, the quantification of the input parameters, and then finally the calibration and the interpretation of these models. So testing the sediment flux. This was the first hypothesis. So this video shows that during early falling stage, we have a mixture of hemipelagics and sands through the basins, labelled here. And then during maximum low stand, we have an influx of sand into the model. And then this is shown with the fast use definitions. We've got a mixture of sand and turbidites in Basin 4, with the sandy channels interconnecting these. And then during maximum low stand, we have sand and lost turbidites incorporated. And then the nested model, this video again shows very similar. We've got a mixture of muddy turbidites, mainly muds within the 3 basins. And then during maximum low stand, we've got large influx of sand into the model here. So looking at these cross sections, we are comparing the regional and the nested model at early falling stage and then maximum low stand. So you can see here in the regional model, we've got a large influx of mainly silts and some sandy channels in Basin 4. This is compared to the last glacial maximum, where we've got a large influx of sandy channels in Basin 4. And the same can be seen looking at the Fatty's definitions for the nested model. So comparing the 2 Basin 4s at the different ages, we definitely see large influx of turbidites during maximum low stand as compared to early falling stage. The testing hypothesis 1, which is the impact of use to sea on MTDs within Basin 4. You can see that between the early falling stage and that maximum low stand, you can see there's really not much difference between all the 3 basins, the geometries, the Fatty's and the core sand percentage. This tells us that there is minimal change in the models when use to sea varies plus or minus 10 metres. Therefore, this suggests these results are within the sensitivity of the Miller 2020 sea level curve, which is what we'd like to see. And finally, the slight increase in sands and turbidites when you static sea level minuses 10 metres, which you can see here in this final diagram, indicates that perhaps use static sea level, when other parameters are kept the same, there is a dominant control. Testing hypothesis 2. So this is testing the impact of the allocyclic versus the autocyclic responses, sediment supply, fluvial discharge. So you can see here, when comparing the base case model E and model F, you can see that during early falling stage, you've got minimal turbidites, but a lot of mud into the model and some channels, especially in model F. But during maximum low stand, you see a large influx of turbidites, mainly within Basin 4. This is demonstrated in the cross sections below. So you can see that comparing the base case model with models E and F, model E shows a large amount of unconfined turbidites, perhaps slightly muddy with some sand tunnels, whereas model F, so fluctuating sediment supply according to literature review, demonstrates that you seem to have a large proportion of unconfined turbidites, and perhaps these are muddy as well. So comparing the regional model at 22,000 years ago with model G, increasing the storms, we have an interesting development. We can see that you've got some point bar deposits towards the coastline, and then increasing remobilization of finer sediments, including mud, and then some coarser sand into Basin 4. When comparing the Fatty's, you can see that you've got a high proportion of turbidites, and we would estimate these to be muddier. However, you can see that there are sand channels above, so perhaps there isn't a seal on top of these. So the Fatty's calibration of model A, you can see that we've got very similar thicknesses across the 3 wells. These were from the Expedition 308 wells. However, you can clearly see the influence of the difference in resolution between the observed results in track 1 and the simulated results in track 2. So you can see that track 2 has a large proportion of especially sandy channels in U1320A compared to the mixture of silts and sands in track 1. And this can be changed utilising the influence of seismics and also looking at the diffusion coefficients. And you can see that their locations here. The regional calibration, the wells A to C were interpreted using the resistivity, the sonic and the gamma ray, and correlated across the section, and you can see here. So to your right, you can see the large model and the base case model, and comparing the Fatty's proportions. So you can see that during early falling stage systems tracks, you have a large increase in silts, and this is compared to the maximum lowering of sea level, for that short time period at 20,000 years ago, between units 10 and 11, where you've got an increase in sand, but perhaps a decrease in turbidites, which indicates that these are perhaps more muddier turbidites in our model than predicted. So you can see again the average sediment proportions between the large and the small model, and this is shown more clearly. You can see an increase in coarse sand and sand at 22,000 years ago between units 10 and 11. So the Cougar flow analysis of the testing of the sediment flux can be shown below. So these are the three 308 wells. You can see that whilst there is a difference in resolution, you can see the thicknesses are relatively similar. So these are the thickness error maps. So the yellow and red indicates that the sediment is too thick, whereas the black and blue indicates areas where the sediment across the model is too thin. And the reason for this is it could be due to the energy of the model. So perhaps the diffusion coefficients were overestimated. So further work would seek to reduce these, incorporate more silt into the model, and perhaps these error anomalies would reduce. So this is the uncertainty parameters for the Pleistocene mean total thicknesses of the model, in particular the regional model, and the core sand average uncertainty parameters. So you can see that sediment supply and discharge, including transport processes, were the most uncertain parameters. And the reason for this could be down to the diffusion coefficients, whereas sediment supply and discharge came from literature. So I believe that incorporating seismic interpretation into this will hopefully reduce this error. So hydrocarbon implications. We can see from the Pseudoworld log that we have around 100 metre thickness of an MTD package, and generally this is quite sandy, which indicates a good quality reservoir and hopefully good porosity. However, the influx of mud could reduce its reservoir quality. So there are two factors determining the reservoir geometry. So we have unconfined MTDs, which are smaller in volume and lower in efficiency, which indicates a poorer quality reservoir. And we have confined MTDs, which seem to be more present in the regional model, which are larger in volume and higher efficiency, remaining in Basin 4 rather than pinching out across the sea. See this here. We've got some pinching out towards the base of Basin 4, and as you can see, there is perhaps no silt above, which indicates perhaps there is no seal. So you can see this turbidity indicator graph for the nested model, Model B, indicates that most turbid sediments occurring during early falling stage system tracts, and this is compared to the increasing storms, Model G, whereas during the lowering of sea level, this is when you've got most turbid sediments. This indicates that MTDs seem to be present across the whole full eustatic cycle. So conclusions. We can reject the first hypothesis. Therefore, models suggest that the MTDs can occur during both sea level low stands and high stands. And we can see that MTDs are occurring across the full eustatic cycle. Furthermore, we can reject the second hypothesis. Whilst UCC is a dominant factor, its alterocyclic controls such as sediment supply, storm frequency, and local interactions with topography, which we can see through the following models, influence the MTD sedimentation, geometry, and lateral descent. Finally, the impact on hydrocarbon migration. We have two models from Burgess and Hovis and Johannesson and Steele. So the high stand MTDs are thinner, muddier, and therefore a poorer quality reservoir we predict, whereas the low stand MTDs are predicted to be higher quality reservoirs, and they are thicker and more laterally continuous. However, this lack of pinch out could lead to a lack of stratigraphic flux. The recommendations and further work. We have 4 recommendations. So firstly, I would incorporate more in seismic interpretation, which allow enhanced understanding of facies geometries and therefore a paleobathymetry to be further constrained. I would reduce the diffusion coefficients, therefore allowing more silt to remain in the model. Thirdly, I would integrate more subsurface data from the wells close to Basin 4. This would increase the calibration and accuracy of both the facies and the thicknesses, therefore allowing more reliable understanding of the evolution of the facies. Finally, I would increase the sensitivity analysis, incorporating 100 simulations instead of 13. This is reliant on computer power. However, this would increase the predictability of the response surface and determine the most significant factor with more reliability. Do you have any questions? I also have some backup slides if anyone's interested in viewing them. Thank you very much.